So probably we should get started. Many of you heard about the UCAR community program called UCP. The UCP was established in November 1992. But in fact, the program actually started, some of the program of UCP actually started as early as 1981. And the first one was it's called International Program Office, which was the former name of JAS. So even though the UCP, UCAR Community Program, has been in existence for quite some time, I was sometimes kind of shocked that people said, Bill, what is UCP? Even some of the NCAR people who have been at NCAR more than 25 years do not know what is UCP. And so this year, we have a special celebration of the 25th anniversary of the UCP. And yesterday, we had a great program with invited speakers from, for example, Dr. Eric DeWeaver from NSF, who supported the CRIBA program, supported the cosmic mission. And today, it's our special seminar in celebration of 25th anniversary of UCP. And so when Adam Thomas, who is helping us setting up the seminar, was saying, okay, Bill, shall we say this is a UCP seminar series? I said, well, this is actually the first one in 25 years. I'm not sure when will be the next series, maybe another 25 years. I hope it's more than frequent than that. So this is a very important celebration. And the reason why I want to do this special seminar here is exactly what I said. A lot of people do not know what is UCP. And in fact, as you know, we have a national center, NCAR, and it's like the 800-pound gorilla within the UCAR organization. People heard about NCAR and do not know that actually UCP does a lot of very important work that support, enable, and serve the science. And one of the services that we provide is actually to support very important interagency science programs. And one of such programs is called the US CRIBA, and it's a national research program designed to investigate the variability and predictability of the global climate systems on seasonal, interannual, decadal, and centennial timescales, and with a particular emphasis on the role of ocean and its interaction with other parts of the Earth system. And the US CRIBA was created in 1998. And believe it or not, the JAS, and the one called CPAS, has been managing it since 2000. And many of you saying, well, why is this important? Because in my opinion, is through the service that we provide from people, the UCAR staff, like Mike Patterson, who is a director for the program, and Kristen Udenbrock, who is the special program specialist, and Jill Reinsdorf, they are providing this important support and service so that we can have these important national CRIBA program be functioning effectively. And just to show you how our service have impacted the science, I just heard from Paul and Kevin, this special working group called the Working Group on the Changing Width of the Tropical Belt. In 2 years, this working group has published 13 papers. And that's the reason why we're holding this seminar on the 13th of October. We'll publish, okay. So, it's important for us to realize, even though we do a lot of work, we come to work 8 o'clock, go home, and very often we have to be, organizing meetings, writing memos. But it's very important for us to know that our work does impact the science that we do, and we should be proud of what we are doing. And today, to show you the impact that one of our program, US CRIBA, that we support, their impact on the science. I'm very pleased to invite Professor Paul Staten from Indiana University, and Professor Kevin Grise from University of Virginia to give this spatial seminar, Tropical Widening, What, When, and Where. Professor Staten received his PhD in 2013 from University of Utah, and Professor Grise got his PhD from CSU in 2011. And a very important reason also about our for this seminar is also related to other program that UCP is providing. That is the COSMIC program. And COSMIC, as you know, started from 1992 with the launch of this GPS MEDTEC mission that demonstrate how radial occultation could be used. Could be used to study the troposphere, the stratosphere, and ionosphere. And in fact, one of the most unique aspect about COSMIC is it's a SI. It's a unit measurement. That's one that could be fundamentally based on the SI unit, which is the time. And it's been called the world's most accurate thermometer for climate change. And so when you are interested in studying the widening of the tropics, and I think that radial occultation data, both from the tropopause perspective and also from the low-level water vapor perspective, could be very valuable for the study of the widening of the tropics. And that's also the reason why we really need to keep going with this very important observational technique. And another very important reason here is that the COSMIC-2 mission will be launched in June next year, and it will be providing 5,000 occultation soundings from 40 south to 40 north. And so this will be valuable data set for us to see how the widening tropics is impacting the weather and climate processes. Without further ado, I'm going to introduce Professor Paul Staten, and later on, Kevin Grise will be continuing. Thank you.
Thank you, Bill, and thank you all for coming this Friday afternoon during your busy weeks. To hear something that I'm passionate about, I'm excited to share this with you and acknowledge everyone, welcome everyone who's tuning in online. Welcome. Bill, it's exciting to hear about to COSMIC-2. As a master's student, I worked with data from COSMIC-1 back when it was new. And it actually indirectly led to the research that I did as a PhD, which relates to what we're talking about today, the width of the tropics. So when we say the width of the tropics, what do we mean? If you do a Google image search, you will see coral sands and palm trees, which we could all use a little more of. But if you look at a map, when we say the width of the tropics, we are usually talking about an expansion of the poleward edges of the tropics, or basically the subtropics. When you look in the inner tropics, the deep tropics, you have the Amazon rainforest, you have the Congo, and you have Indonesia, more of what you may think of when you think tropics. But if you look at the borders of the tropics, you have the Saharan desert, or the Arabian desert, the Great Indian Desert, the Gobi Desert. Or if you look in the southern hemisphere, and the Sonoran Desert, in the southern hemisphere you have the Australian outback, the Namib Desert, and the Chilean Desert. So that's the news, is that if the tropics are widening, we can expect, first guess, to see an expansion of this type of climate. So if you look at climate zones, you can see from this Köppen classification map a band of red and pink shades going around the tropics. That's your lush, moist climates. And then on either side of those, you have a lot of yellow shading. So this is your dry, hot desert climates. And this map is summarizing climates from recent decades. But if you look at the end of this coming century, these climate zones are going to shift. How much they shift depends on our choices. But you'll notice if I switch back and forth between these figures, looking at the subtropical climates, in addition to subtle expansion in most areas, there are a few areas where the expansion is pronounced. And even what looks to be a subtle expansion is still an expansion on the order of a few hundred miles. And these are often in some of the more populated regions of the world. So as far as impacts go, widening of the tropical circulation could have profound impacts on humanity. For example, the New York Times had this article, Living in China's Expanding Deserts. They did a great job putting a face to this problem of desertification. So they featured a family and groups of families and farmers living in China. Actually, China's government is very aware of this problem. They pay families to grow, to plant and to grow in the neighborhoods of these desert climates to help slow down the expansion of these desert sands. Other ways we can see this expansion of the tropics from observations include a change in ozone. Ozone is mostly in the stratosphere, and up in the stratosphere it protects us from the sun's ultraviolet rays, which is great. Most of the ozone is in the polar latitudes. Over the tropics, the troposphere, which contains our weather, is taller, and there is less of the ozone-containing stratosphere. So if the tropics are widening and the high troposphere is widening, that means the amount of stratospheric air you have is, over certain latitudes, is decreasing. The amount of ozone is decreasing with that. Similarly, if you look at the purple dash curve, the tropopause, which is the boundary between the troposphere and the stratosphere, is higher in the tropics, and that high tropopause is expanding as well. Both of those changes indicate a widening of the tropics. You can look at the green line, which is outgoing long-wave radiation. It's how much heat the Earth is giving off to space at different latitudes. By that, the tropics look, again, to be widening. If you look at where the most outgoing long-wave radiation is occurring. Also, the subtropical jet streams, which occur on either side of the tropics, have been getting further apart. And finally, there's the Hadley Circulation, which I'll talk about in the next slide, which seems to define a lot of the climate we experience in the tropics and subtropics. All these metrics show widening, but widening at different rates. The Hadley Circulation is this construct that we've been using to understand climate for centuries now. This, from the Mystery of the Expanding Tropics article, the Hadley cell is visualized as an east to west band of rising air in the deep tropics, which rises and it gives off much of its moisture as rain as it rises, and as the moisture condenses and falls out, it leaves behind some of its heat. This air then rises poleward to about 30 degrees north or south before it sinks again, and as it sinks, it warms back up. Plus, it has that residual heat left behind by the precipitation. So as this air reaches the surface, it's very warm and dry. And then this air is brought back towards the tropics, and any moisture you had in the soil or on your skin, if you're living in the subtropics, this air is very good at taking that moisture and taking it back to the deep tropics. Chen Liu, in 2007, gave us some of our first understanding of the widening of the tropics from model data. So you can see the expansion from precipitation. You look at the precipitation minus evaporation field, and you have the climatology outlined in black with a shaded region representing the dry subtropics. And then if you look at modeled precipitation minus evaporation change, the drying is in red and orange, and you can see that this drying belt expands particularly on the poleward sides of these climatologically dry regions. So this was in 2007, and the earlier figure with the several plots I showed you is back in 2008. So back then we had this idea that the tropics had been widening. We had a lot of different ways to look at it, but the widening rates were quite large. A few years later, Sean Davis and others looked more closely at these metrics. Why did some metrics show tropics widening at an incredible pace, others showed it widening at a moderate pace, and some didn't really show it widening at all? They looked closely and they found that you had to be very particular about how you chose your metric. If you chose an arbitrary threshold, it would be sensitive to small changes in one quantity or another. And then once you pick a quantity, you also have to calculate it carefully. And these choices make a big difference. And by carefully controlling these decisions, they were able to narrow down the range of uncertainty in the widening of the tropics considerably, but there is still substantial uncertainty in just how quickly they are widening. And this is part of the mystery of the expanding tropics. At the time of these earlier papers, the general understanding was the tropics are widening, and in a warming climate, think of Chan-Lu's study, you should expect a widening tropical climate zone. So you put these two together, and it seems pretty clear that global climate change should have something to do with this. But we have been learning recently more and more how important year-to-year variability is, even in the width of the tropics. And this is part of the mystery. Why did the tropics expand more quickly in recent years than models appear to suggest that they should? This article cited a Chapman conference in Santa Fe where a bunch of us met to discuss this issue, and there was an emerging understanding from this meeting that more work was needed to refine these metrics, make sure we were all on the same page, and to understand and to quantify more closely how much of the widening is forced by climate change and how much of it is natural. And in response, we formed a working group sponsored by CLIVAR. And here are several of us at our last working group meeting. Some of our group members aren't there, to address these problems. So how do you measure the widening tropical belt? And how much of it is natural, how much of it is forced? And where is it occurring, and where will it have the strongest impacts? So Kevin Grise will talk about these first two problems, and then I'll talk to you again after that. Kevin?
Well, thanks everyone. So I'm going to take over here for a little bit. So my name is Kevin Grise. I'm an assistant professor at University of Virginia. And as Paul said, I'm going to kind of run through some of the methodological details about how scientists actually calculate this issue of how the tropics are actually widening. And then talk a little bit about how we can determine whether the widening of the tropics is due to climate change or it's due to natural cycles in the climate system. Okay. So how do we measure tropical widening? So if you look at this schematic that Paul showed, you can see the Hadley cells, right, with rising motion over the equator and sinking motion in the subtropics. And so basically a simple way you might think, well, we can measure this sinking motion in the subtropics, and where that sinking motion is located, you might be able to sort of measure where the Hadley cell edge actually is. But it turns out that this sinking motion is actually really gradual. It's very difficult with our current measurement systems to measure basically downward motion in the atmosphere. So what we typically do is calculate something that we call a mass stream function. And this requires us not to use up-down motion, but it requires us to know north-south motion or north-south winds in the atmosphere. And so this is what the mass stream function looks like in sort of an annual average, so average over all months. And so the solid contours here indicate rotation in a clockwise sense. So this is the surface, and this is the upper atmosphere on this axis, and then this is the South Pole here and the North Pole over here. And so you can see in the northern hemisphere, right, you have rising motion in the equator, and then south to north flow aloft, and then sinking motion here near 30 degrees. And then the opposite in the southern hemisphere goes like that. right? And so ideally, you want to sort of find where those red lines are, basically, using this sort of mass stream function metric, which again sort of adds up the north-south wind as you go from the top of the atmosphere all the way down to the surface. And so this is wonderful if you have global measurements of the wind field, basically from the top of the atmosphere to the surface, but we really only have that since the advent of weather satellites, which occurred probably about 40 years ago now. So we can calculate what in the lingo is called the psi metric or the psi 500 metric. But it often requires us to have a lot of data over the entire atmosphere. And so a number of different authors, some of which Paul introduced, have started to look for other ways we can define where the edges of the tropics are located. So from the days of early explorers, we know that sort of the surface wind direction is different from the tropics to the extratropics. So in the tropics, right, winds blow east to west. This is why early explorers that went from Europe to the Americas, they went through the tropics. They followed the so-called trade winds that blow east to west. And then they returned to Europe basically using what we call mid-latitude westerlies. So at latitudes here in the United States, for example, the winds blow west to east, right? So you can use that transition from what we call easterlies or east to west winds in the tropics to west to east winds here at higher latitudes. Another feature that we can use is the sea level pressure or surface pressure. So where you have sinking motion in the atmosphere, like we have with the Hadley circulation, you also have high pressure at the surface. And so you can define sort of where those high pressure regions are and whether they're moving around in time. And the nice thing about surface pressure or sea level pressure data is that basically we have long time records. So surface weather stations have been taking sea level pressure or surface pressure observations back into the 19th century. And so this allows us potentially to get an understanding of what has happened with the width of the tropics back 100 plus years in time. And so these surface measurements are a way that we maybe can extend what sort of we learn now with this mass stream function metric back in time. As Paul mentioned, you can also use fields related to the water cycle. I mean, obviously the impacts here, we care about where dry zones are moving around. And so you can actually look at this map here is from a observational-based what's called reanalysis product. So you have precipitation here, right? Heavy precipitation in the deep tropics, higher precipitation in what we call the storm track regions, or basically regions in mid-latitudes where we have a lot of fronts and high and low pressure systems going through. And then you can see in the subtropics here, these regions where you have large evaporation, as Paul mentioned. So these are regions, these dry regions. And so you can monitor basically how these regions are moving around in time using the evaporation and precipitation field. And then you can use the cloud field. So we know that where we have sinking motion in the sinking branch of the Hadley circulation, that we have these dry regions basically, and where there's sinking motion, we tend to have fewer clouds. And so you can see over Africa, for example, on this given day from this NASA MODIS satellite picture, that we don't have any clouds over the Sahara and over the Kalahari and Namib deserts of southern Africa. So you can see that you can potentially use the cloud field to denote basically using satellite measurements if the tropical belt is potentially moving around. You can also use metrics higher up in the atmosphere. As Paul mentioned, the Hadley cell is monitored, is demarked at a higher altitude by what's called the subtropical jet. And this is a region of fast west to east moving wind and around 40,000 feet in the atmosphere. And so this isn't the jet stream that necessarily affects our weather every day here in Colorado, which is called the polar jet. But the subtropical jet is a little bit higher up in the atmosphere and also slightly weaker. But we can use the position of that to determine basically where the edges of the tropics might be. And finally, as Paul mentioned, we can use what's called the tropopause height, right? The boundary between the lower atmosphere and the higher stratosphere where the ozone layer is located. And so this plot from a paper by Diane Seidel and Bill Randall shows that in the climatology, the tropopause is typically around 16 or 17 kilometers or around 55,000 feet up in the atmosphere, right? Versus in the extratropics, the tropopause is more around 11 or 12 kilometers, or 35,000 to 40,000 feet or something like that. And so this is what Bill mentioned at the beginning of the talk, that you might be able to use this new GPS radio occultation data to kind of figure out sort of where the tropics are versus where the extratropics are. So a big problem with this, right, is we're all sort of measuring these different features that are around 30 degrees latitude in the atmosphere. And they basically all have varying time series. So you would think they're all in the same place, and if the tropics are expanding, they would all give us the same answer, that the tropics are expanding by a given rate. But if you look at these lines, you get varying different answers. Some of these metrics give you something around 10 miles or 15 miles per decade, so a very gradual expansion of the tropical belt. Whereas other metrics are giving you something around 100 miles to 150 miles per decade, something much more drastic, that these dry zone regions are moving poleward at a much faster rate. And so as scientists, we've been trying as this working group, trying to understand why there's so much difference here between these lines on this plot. And so what I think a lot of this is the old analogy of sort of, you blindfold a bunch of people and ask them to feel different parts of an elephant, and they all give you slightly different answers, right? And so a big part of this is that we're all looking at the same animal, in this case the edge of the tropics, but we're all looking at different characteristics of that. And so that's giving us all these different, slightly different rates of how fast the tropics are expanding. And so one of the goals of our working group is basically to provide guidance on which of these mechanisms or which of these methodologies we should be using to measure the edge of the tropical belt. And so this is just a brief summary, a sort of a qualitative summary of some really interesting research findings that have come out in two papers that are related to our working group by Solomon et al. In 2016 and Nick Davis and Thomas Berner in 2017. And what this has done is it's gone through these 7 metrics that I've introduced and kind of have compared them, figure out which ones are related to each other. And so a lot of these, for example, the Hadley cell, the trade winds, the surface pressure, evaporation and precipitation, they are highly related to one another. They are strongly correlated with one another. And they're also strongly related with surface impacts. And so if you care about what's happening at the surface, you should care about what these metrics are doing. But surprisingly, these sort of what we call upper tropospheric metrics or upper atmospheric metrics, sort of the clouds, the subtropical jet stream, the higher tropopause heights, actually have a very weak relationship with these surface impact features, and with sort of these what we call, what I'm terming here, red metrics or lower atmospheric metrics, and blue metrics, which are more upper atmospheric metrics. And so the implication of this is that if we move forward and we look at projections from a global climate prediction model, is that over the 21st century, using these different classes of metrics would give you 2 different answers. That basically, if you use the metrics based on the tropopause or the subtropical jet, so these upper atmospheric metrics, you actually don't see much of an expansion at all over the upcoming 21st century. Whereas if you look at these lower atmospheric metrics, which are dependent more on or related more with surface impacts, you do see that there is somewhat of an expanding tropical belt. And so this indicates that the methodology that we use to determine the expansion of the tropics might be very important. And so because these metrics here are so related with surface impacts, I'm going to focus for the remainder of my talk on these what we call lower atmospheric metrics, which are expected to have a trend over the 21st century. Okay, so the next question I want to address then is why? Why are the tropics widening, right? So hopefully we've determined that they actually are widening. So why are the tropics actually widening over the last few decades? And so there's a number of hypotheses in the scientific literature that our working group is trying to sort through and make some sense of. And so your first guess might be that this is related to climate change, to warming global temperatures, to increasing greenhouse gases. And so we know that warming temperatures in the atmosphere do a number of things, but one of the things that they do is they act to stabilize the atmosphere in the in the subtropics. And so what this does is it makes it less likely that weather systems, high and low pressure systems that occur in mid-latitudes, it makes it less likely that those systems would encroach into subtropical regions. And so in a sense, you can think of this warming makes the tropics basically expand. Right? And so that's one hypothesis for why global warming might contribute to a tropical expansion. But it isn't just sort of global warming or increasing greenhouse gases that might be related to an expanding tropics. Other studies have found that air pollution, or what we call aerosols in the atmosphere, are very much related to the tropical expansion problem. And so in particular, something called black carbon, which is basically what is produced from burning wood or burning fuels and diesel engines, releases these little black particles, what we often term colloquially as soot, into the atmosphere. And these black particles, just like a blacktop surface, absorb the sun's radiation very well, and they heat up readily in the atmosphere. And so this warming in the atmosphere due to these aerosol particles has also been proposed to be shifting the tropical belt poleward, particularly in the northern hemisphere where we have lots more air pollution due to more population. And then finally, and this is maybe less, people are less aware of this issue, is that the ozone depletion in the ozone layer in the stratosphere may have also contributed to shifting the tropics poleward, particularly in the southern hemisphere. And so due to the refrigerants and the propellant gases that we used in aerosol cans back in the mid to late 20th century, these so-called chlorofluorocarbons were released into the atmosphere. And these chlorofluorocarbons get up into the ozone layer where they act to deplete the ozone hole, or the ozone layer. And this chemistry is most effective where the temperatures are the coldest. And so that's why we have the so-called ozone hole occurring over Antarctica. And so this strong cold region associated with the ozone hole acts to pull the entire atmospheric circulation further poleward. And one of the things it does in the southern hemisphere is cause basically a poleward shift in these dry zones. So all three of these things, sort of warming temperatures, air pollution, and the ozone hole, have been proposed to contribute to the recent trend in basically the edge of the tropics. And so if you plug all of these things into a global climate prediction model, so the greenhouse gases, the air pollution, the stratospheric ozone, and you average a bunch of models together to basically get a consensus opinion, how much do these, what we call forcings, matter for shifting the tropical belt? This red line here is just from greenhouse gases alone, and the green line is from basically all three of these forcings. And so you can see that yes, climate models give us sort of a small shift in the tropics, but again, it's toward the smaller end, right? Sort of this 10 to 15 miles that we've been talking about. But here, if you look over here, these are observational estimates. I believe these use the Hadley cell or the stream function metric. And you can see that these, based on observations, are toward the higher end, so toward more of this 100 to 150 kilometer range in the tropical belt. And so it's often reported in the news, in the scientific journals, that basically models cannot capture the magnitude of the tropics widening that we've seen in recent decades. And so the big question for our working group is, what is missing here? What is going on? And so I think what has come out of the science in the last 5 years is really sort of the role of natural variations in the climate system, and in particular something that we call the Pacific Decadal Oscillation, which I'll explain in a minute. And the basic idea is that these natural oscillations in the climate system also can move the tropical belt around in time that's not necessarily related to climate change, but is related to sort of natural cycles in the atmosphere and ocean. So I suppose many of you in the audience are familiar with the El Nino Southern Oscillation, which refers to a periodic warming of the ocean waters off the west coast of South America, off the coast of Peru and Ecuador here. And so when these temperatures warm up, this is referred to as an El Nino event. And in this time series here, the orange shading indicates El Nino events in time. So when an El Nino event happens, multiple global impacts occur, including sort of heavy rain in parts of California, drying in Australia and Indonesia. But one thing that many people are not aware of is that an El Nino event actually contracts the tropical belt. In other words, moves these subtropical dry zones further toward the equator. A La Nina event, which is the opposite of an El Nino event, cools these ocean waters off the coast of South America here. And so a La Nina event would be associated with an expansion of the tropical belt in this region. Okay, so this is sort of what we refer to as shorter timescale variability in the ocean. So there's something that's maybe less familiar to people, which is called the Pacific Decadal Oscillation. And the PDO is very much like El Nino, but occurs on a decade-to-decade timescale. And so when the PDO is El Nino-like, what we refer to as the positive phase, that is associated with a contraction of the tropics. When the PDO is more La Nina-like, it's associated with an expansion of the tropics. And so if you look at the time series of the PDO here, the PDO was very positive, more El Nino-like during the 1980s and the 1990s. But since sort of the late 1990s or the early 2000s, the PDO has been more La Nina-like. And so this trend on its own would lead to basically an expansion of the tropics, because it's going from more El Nino-like during the 80s and 90s to more La Nina-like during the 2000s. And so this is in fact what a recent paper by Bob Allen, who's one of our working group members, has found, that if you force, so these are the observational estimates of how much the tropics have widened by degrees latitude per decade. So you can see that they're highly variable, just as we talked about earlier. What he's doing is he's forcing a climate model with the ocean temperatures caused basically by global warming, by climate change, and those caused by the Pacific Decadal Oscillation, or this negative phase of the PDO. And so these light blue lines here indicate the tropical expansion that would be driven by climate change in this particular climate model. And you can see that they're generally relatively small and less than what you see in the observations. And you can see that in both the northern and southern hemisphere. If you go over here, this is the rates in the tropical widening that are due to this natural cycle, the Pacific Decadal Oscillation. And you can see that some of these bars are much larger than the bars over here associated with climate change, and even reach some of the levels that you see in the observations. And so the conclusion that he comes to in this paper is that we really need to consider natural cycles, in particular this Pacific Decadal Oscillation, that at least some fraction, maybe even a majority of the recent tropical widening has actually been associated with this natural cycle in the ocean. Okay, so now that I've asked that question, then what's going to happen in the future? So we've talked a lot about what we've observed over the last 30 to 40 years. So let's talk a little bit about what might happen in the future. So these are relatively busy plots from a paper by Tao et al. But for our talk today, I only want you to focus on the light blue line, which is on the top on each one of these panels. So this is Northern Hemisphere winter, spring, summer, fall. This is a time series at the edge of the tropics from the present to the year 2100. And the point here is showing that the light blue line indicates what we call our indicates worst case scenario for the 21st century. And in the scientific lingo, what we call RCP 8.5. So it's a strong warming of the climate due to climate change. And what you'll notice here is that in the northern hemisphere, the tropical belt has an interesting seasonality, that yes, there is some expansion in most seasons, although not in summer, but it's relatively modest, that it's only during the autumn months, during September, October, and November, that the expansion of the tropics is the largest. All right, so there's an interesting seasonality there that we still are trying to understand as a working group. The other thing to note is that the largest effects are going to be in the second half of the 21st century. So you can see after this dashed line here, which is the year 2040, the trends really start to become much larger. In the southern hemisphere, all right, so these are same plots in the southern hemisphere, you can see that the seasonality is much less, so all 4 seasons look about the same, but the same conclusion holds basically, that the expansion of the tropics will be largest in the second half of the 21st century. So to try to put sort of a statement here, it's saying that if we're thinking about tropical widening in the present, we have to consider both natural cycles and sort of climate change impacts when we consider understanding what the recent effects or recent changes that have been going on in the subtropics. So with that, I'll turn it back over to Paul, who's going to talk about more of an impact standpoint. Where, in fact, do these changes matter? So we've determined sort of that the tropics are widening and maybe why they're widening. So where does this actually matter?
Thank you, Kevin. And I'm going to leave it at this slide for just a second to illustrate one more point, and that is that the Hadley cells, the tropics, are different from one season to the next. Some of the weather patterns follow the sun, so their mean climate is different, and their trends are also different. So when we talk about where tropical expansion will have its greatest impacts, that's going to depend on geography. It's also going to depend on the time of year. So I'm going to give you a tour of planet Earth, at least the land-covered third of it. And the images I'm going to use here are going to come a lot from the NASA Visible Earth Collection. And on top of that, I'm going to draw some cartoony arrows, blue for the winter hemisphere Hadley cell, and orange for the generally weaker summertime hemisphere Hadley circulation. And these are derived from the Psi 500 metric, but a variant that works locally. I'm going to use outgoing long radiation cutoff from Chen et al. 2014. So these are going to be time series estimates of regional widening of the tropics based on the outgoing long wave radiation. I'm also going to show you some schematics of trends in tropopause heights measured by weather balloons from Lucas et al. In 2015. And for your reference, I believe this was the torso of the elephant, and OLR was the trunk. And finally, maps of the subtropical ridge, usually a high pressure center is associated with nice balmy weather. It's also associated with that clear skies in the tropics, so it makes a great measurement of the width of the tropics. So in these small maps, we'll have the subtropical ridge in black, and that's the west to east ridge in the green curves. You could think of those as the pressure topography map. That topography is changing in time, pressure patterns are changing, and that's shown in the shading. So first up, South America. We'll start next door, we'll work our way around the Earth and come back. Over South America, during the dry season in the Amazon, the wintertime Hadley circulation is basically importing dry air from the north, and it's sinking, suppressing convection over a good portion of the Amazon. During the summertime, the southern hemisphere, summertime, the Hadley circulation is bringing moisture to the Amazon where this air rises and then exports dry air to either direction. So if you look at the limits of the Hadley circulation over South America, during the winter, it's right here, partly in Brazil, and then during the summertime, it's here just south of Uruguay. So if you're going to talk about the impacts of any Hadley cell widening, it's going to depend strongly on the time of year. So let's look at some of the changes. If you look at OLR, it looks like the South American Hadley circulation has been shifting poleward in observations. So OLR shows it shifting poleward. If you look at the tropopause height in weather balloons or radiosondes, you also have between a 0.4 to 0.5 degree shift per decade, but there are data issues with the radiosonde database over South America. So there is some uncertainty in that. Also, the author notes that ENSO, the El Nino Southern Oscillation that Kevin mentioned, plays a big role in the tropopause heights over South America. And finally, looking at that pressure topography, what you're looking for here to see a southward shift are green circles or with red shading to the south. Or if you look at the black line, look for red shading at and poleward of the black line. And you may see something, but there's not a clear poleward shift right over South America, but perhaps that's because it's getting smeared during the course of the year. So that seasonal cycle is crucial. Over Africa, Africa is big enough that it gets the Hadley cells year-round. So during Northern Hemisphere wintertime, the Southern Hemisphere Hadley cell, the summertime Hadley cell, is over the Kalahari Namib deserts, and the wintertime Hadley cell terminates over the Sahara near the Mediterranean. And then during our summertime, the situation is basically reversed, but the Hadley cell edges both terminate basically over Africa. Now, Africa is so big it gets a few extra slides. Over the Southern Hemisphere, it's hard to tell if the Hadley cell has been widening if you look at OLR over Africa. Northern Hemisphere, on the other hand, it looks like it has been widening from OLR. Radiosondes, similar picture, the tropopause height. So the Southern Hemisphere, ENSO doesn't really have much of an effect, but we also don't see much of a shift, maybe 2 or 0.2 or 0.3 degrees. But again, there are data issues with the radiosonde data set over Africa. Over the Mediterranean, we see a larger shift, but then you have the North Atlantic Oscillation, you have all these other phenomena with great acronyms affecting the tropopause height over North Africa and Europe. But again, there seems to be an agreement that there is more significant widening over the northern part of the African continent. And finally, if you look for a black ridge with red shading poleward of it, so over over the Southern Hemisphere, if you look a little west or east of Africa, you can see that pattern. It's not clear over Africa. And over Northern Africa, you can see there's strengthening high pressure over the already dry Sahara. So for Africa, it looks like the impacts are probably largest in the northern part of the continent. And so you have the populated regions along the Mediterranean coast that are liable to be impacted by an expansion of the tropics. But there's also a contraction in the rain belts occurring at the same time that's going to affect populations on the fringes of the Congo and the Sahel. And so a theme that's going to pop up several times here is that the Hadley cell widening is not the only player. If you look at Australia, Australia is probably the one place where the seasonality may not matter so much, because during the summer and winter seasons, the Hadley cell basically terminates at the same latitude over Australia. And I was looking at my data and I drew these arrows and I thought, is that true? Let me double check. And indeed, the Australian outback doesn't have a wet season. It has a hot season and a less hot season. And it does look like the Hadley cell may be widening from OLR. If you look at radiosondes, again, it looks like it may have been widening. The trick is that Australia has been getting hit not just by global climate change, forced climate change, it's also been getting hit by changes forced by ozone depletion and by El Nino. And if you look at that pressure map, instead of seeing a clear poleward shift in the pressure, you may see something like a western shift. So there are other regional shifts that can occur in addition to just a poleward shift. Southeast Asia is a prime example. During the summertime, an example of seasonality, the Hadley cell is not really well defined over Southeast Asia. During the wintertime, it's much more well defined, bringing moisture towards Indonesia. So it looks like over the Northern Hemisphere, the Hadley cell is widening in the Western Pacific and over East Asia. Radiosondes show the same thing, but again, these data are strongly affected by ENSO and the PDO. And if you look at the pressure patterns, instead of seeing a clear widening, you have something that looks almost like a southeastward shift of the subtropical high, which is a little different from what you'd expect from a straight zonal mean warming. And this agrees with the pattern of desertification seen over China, at least from that New York Times article, sample size of 1. They were showing desertification in the Ningxia province, which is southeast of the Gobi Desert. So there's actually desertification going to the southeast. So when you're dealing with topography, the Himalayas, and these complex land-sea geography, interpreting a poleward shift in the Hadley cell and its impacts gets very challenging. Let's work our way west back towards, case in point, of what's going on over Asia. Besides just the Hadley cell warming, in a warming climate, you have warming over the surface in particular. So if you look at this time series, in the top plot, if you look at land surface temperatures, we have an increase in recent decades, getting stronger over the next several decades. You look at precipitation, precipitation took a dip in this record, and then it's projected to increase. So some areas can expect to get more precipitation. On average, precipitation increases over land. However, that increase in precipitation does not keep pace with the increase in temperature and aridity over land. So what you get is even regions that are getting more rain, a lot of those regions are just so much warmer that there's increased evaporative demand in those areas, and the rain is just not keeping up. So that's another possible player for the Gobi Desert in East Asia, for example. Europe, as I showed you, was a little bit north of the terminus, the end of the Hadley cell. I stated earlier that it descends over Africa. One trick is that the Hadley cell is not the only cause of descending air. The mid-latitude jet also produces a circulation, and that includes descending air on the poleward side of the Hadley cell. So, as I showed you before, there is Hadley cell widening south of Europe. Weather balloons also show a widening, but it's not clear that what we're seeing is Hadley cell expansion over the European subcontinent. So there are other players acting here, particularly the mid-latitude jet. This is the same story with the North American continent. If you look for a local Hadley circulation over North America, the best you're going to get is something like a small summertime circulation over about eastern Mexico, and then a small wintertime circulation around Baja California. Really not much to understand in the context of the Hadley circulation. But you do have arid and semi-arid climates, and these are associated with the mid-latitude jet. So even if the East Pacific Hadley cell is widening, over the continent, radiosondes and weather balloons don't show really strong widening over the United States. They may be 0.2 to 0.3 degrees, but it's not statistically significant when you think of the year-to-year variability. And again, the Hadley cell is not well defined. Instead of a straight west-east black line with high pressure to the north, it's a bit of a mess. Climatologically, what we see is high pressure over southwestern United States, a pressure ridge, and a jet stream that tends to dip down east of the Rockies. And this is probably a better framework for understanding impacts here at home. The Hadley cell widening is part of a whole system, of a global system of circulation changes. So in summary, what is tropical widening? The subtropical dry zones are expanding poleward. It's been happening over the past 30 or 40 years, but it's really anticipated to pick up towards the end of this coming century. And the impacts of this are going to vary greatly by continent, but in particular, South America, Asia, Australia, and Africa are likely to look at as hotspots, if you will, from Hadley cell widening, where the impacts will likely be severe. And why has it been occurring? It's been a combination of natural variability and climate change. And natural variability is particularly strong and impactful when you're dealing with decadal timescales, like what we've observed. But once you start looking at century timescales, it starts to get less and less about that year-to-year variability and more to more about our decisions. So, thank you very much.
So, let me ask you a question. So, one of the diagram you show that there are difference between model and observation. And when you say model, is this the free-running climate model that doing decadal simulation, or they are not analysis, right? They are truly the free-running model prediction, right?
So yeah, so I guess so. Let me go back here.
That it was a diagram showing the difference between model
Yeah, so I can explain so a little bit back here. This one.
Yep.
Okay. Yeah, so these are models that have their own what's called dynamic ocean, basically, right? So fully coupled models, right? So the lines over here are models with a fully interactive ocean. These, from Bob Allen's paper, are runs in which the sea surface temperatures are prescribed, basically either to this mean sea surface temperature trend or to this PDO type pattern. So the argument is that if you prescribe the sea surface temperatures to closer to the observations, you're able to get closer to the observations that way. So yeah.
But I saw when you say that the forced SST was unforced SST,
right.
My interpretation that unforced is that you allow the ocean and the...
Let me explain that a little. Again, it's not my paper, but so what he does is he takes the total trend, what you would get from observations, then he takes the climate model mean, right, and that's considered to be the forced, and then he subtracts the forced from the total, and that's what he calls the unforced. So it's really an observed trend with the forced response subtracted off. Yeah.
Okay.
Yeah.
So going back to the previous one that's showing the comparison between model and observation, can you explain or some hint on why the model did not capture the observation?
Well, so remember, this is the mean. This is the average of all models, right? So it's not showing the spread. So there might be one model that's right up here, but that's not shown in this figure. So that's the key, right? You don't want to compare the mean, the average of the models. You want to compare all the individual models with the observation.
Are there a model that actually capture these variabilities?
Yeah, yeah. I don't know if that's not on his figure though. Yeah, I don't have the figure on here. But
there are some models?
Yes, there are some that in this sort of large, CMIP ensemble, there are some, yeah.
Must be the ENCA model, right?
Yeah.
Questions?
I think you mentioned that our best bet to have a longer term view than say like just going back to the 1980s is sea level pressure measurements.
Right.
Unless I missed it, you never showed any Hadley Circulation widening metrics going back further than 1980s.
So this is what we're actually working on right now as a working group, is to try to see if we can take these things back. I think sort of my perception is these things have a lot of multi-decadal variability, similar to what I was arguing at the PDO, that there's not a consistent long-term trend. So I think, is that a fair assessment? I was thinking it's sort of what yeah. So.
And maybe just briefly, the figure we looked up before from Alan and someone, the southern hemisphere doesn't do well even with the prescribed SSTs.
Right. So there's no forcing in this model. Okay. And so the ozone hole in the southern hemisphere is a big. So if you don't include the forcing, it suggests that there might be something else going on, right? And presumably with the greenhouse gases, the forcing is included at least in some way in the force response. So that suggests that radiative forcing itself, presumably ozone in the southern hemisphere, because there's not many aerosols, anthropogenic aerosols down there. So yeah.
To add one tidbit to that, the middle and the right columns here are showing the model response due to the forced sea surface temperature pattern and the unforced sea surface temperature pattern separately. But those are both only part of it. You have to, if you want to get the idea what the model with observed sea surface temperatures would see, you basically have to add the middle and the right columns together. So it's still underestimating it. But when you add them together, it improves the picture a little bit.
Okay.
Yeah, there should be a sum.
Any questions? Yes.
So you show that you showed a completely opposite trend when using the different types of metrics to indicate the tropical widening. Particularly, I noticed that if you use the upper troposphere metrics, you show the contraction, and if you use the lower troposphere metrics, then it showed the widening.
There's no contraction there. It's just centered about.
Oh, okay.
Yeah.
So is that possible to reconcile this? Is that possible that the Hadley cell or the large-scale circulations has been twisted because of the whatever the reason is, like global warming or something, so that you get the completely different results here in the upper troposphere and the lower troposphere. Is there any way to look at the vertical thing so that you can make sure the sail, the shape of the sail has not been like twisted or something?
So I'll start with that by saying that, yeah, sorry. I'll start by saying that basically that, so the question was basically sort of why are the upper and lower tropospheric metrics, giving us different trends? And so I think it's actually sort of from a physical sort of dynamic atmospheric circulation characteristic of just the atmospheric general circulation. So you can start in a control run of the model, which has no forcing in it. And if you do correlations between interannual variability between the metrics, they are uncorrelated in these control runs. So right before you even worry about how climate change is going to affect the cell, what we're saying is that even in the control run, right, these two different things that are climatologically in the same location vary with different phenomenon, basically. So I think that's why it's a physical reason why. And so we're trying to understand sort of the physical mechanisms why they are different. But I think you can see even in a control run that they're different. So
another quick question is that the results you show for the metrics, it's the annual mean, right? So have you looked at the trend at like in different seasons so that some of them may be consistent, some of them may be inconsistent?
And that's all included, and that's part of what we're doing as a working group. I mean, in short, it's extremely complicated. I wish I had Darren's sort of. So, but we have like 13 by 13 matrix of all these things. Anyway, I mean, it's extremely complicated, basically. You can read our paper when it comes out. So.
Okay, thank you.
Yeah.
I think that brings up an interesting point, too, that the seasonality. Different forcings have a different seasonal effect on the Hadley cell in the northern and southern hemisphere. So, for example, ozone depletion affects the southern hemisphere Hadley cell very strongly, but only during part of the year. So this is one of the clues we can use to unravel the different causes and effects.
Any other questions? Yes, please.
I was just curious, is that the Who et al. 2013 figure kind of the state-of-the-art expectation for what we can expect? Or I'm just wondering, what are the confidence levels for this, and is it bankable? Like, could we tell people, say, if they're going to have a forestry plantation, that it's a bad idea to put it there because in the next 30, 50 years it's going to be bad? I'm just curious how actionable and how confident these projections are.
Yeah, so if you talk about impacts, I mentioned earlier that land is going to be getting warmer and drier generally. And this is something that models can say with confidence. So there are definitely regions where you can look at these regions on the fringes of the subtropics and you can say, by the end of the century, your crops may need to change, your methods may need to change, or you may need to do these crops somewhere else. There are regions where that type of information in particular is actionable. For the Hadley cell itself, on a regional basis, that's what we're chasing down right now. Is we have a pretty good idea that the southern hemisphere Hadley cell, for example, has widened, and we're confident it's going to widen. But over which regions is it going to widen the most? And what does that mean for these regions? When the global Hadley cell widens, what does that mean for precipitation from one region to the next? And of course, that's a boots on the ground important question to answer. And so I'm glad you asked it. We're asking it too.
Any other questions? So if you look at the longitudinal space, which part of the globe is experiencing, is having the most evidence of widening along the longitude? I mean, yeah.
I guess the first answer to that is probably the Pacific. If you look over the ocean, the Pacific. That also depends on the time of year. Also, over land, a lot of what we average from west to east to calculate the zonal mean Hadley cell, a lot of that is due to the Asian monsoon.
So given that we will have the radio quotation data, how do you see will we best use that data to help study this? I just kind of get your thought on that.
I think that sort of so the question is sort of how can we see sort of the GPS data being used? I think one of the problems we have with this tropopause metric is sort of, particularly in observations, is being able to define it well. That there's not sort of either the spatial coverage or the vertical resolution that you need to find the tropopause. And so that might be more helpful, particularly in regions where we don't have radiosonde launches, weather balloon launches from the surface. So.
Over the ocean.
Yep, exactly. Yeah. So,
any other questions? If not, I'm going to, as a celebration of the 25th anniversary, the first ever UCP seminar, I'm presenting you a special gift.
Oh,
thank you.
Yeah.
Thank you, Paul.
Thank you.
And let's give them a round of applause. Thank you for coming to the seminar. And that's the end. Thank you.